I've been instructed to project, so if it gets too loud for anyone, let me know and I can project less. Well, okay, yeah, well, touche. Okay, so what I'm going to tell you about in this set of 3 tutorial lectures is the ongoing effort in my group and around the world to make quantum matter out of light. And I think this is, in some sense, a nice microcosm of the whole synthetic matter effort, in the sense that we are still building up many of these tools, and this idea that physics is in some ways the same across platforms, whether one's talking about electrons in a solid, or cooled atoms in an optical lattice, or optical photons or microwave photons. We can build many sort of similar analogies. And some of the excitement is the similarities between these analogies, and indeed some of the excitement is you try to force the systems to be the same, but indeed there are important distinctions. And so exploring the places where the physics ends up being different can tell us interesting basic things about the science as well. So I wanted to take a brief moment at the beginning to talk about how to listen to these talks. No, I'm just kidding. I'm just kidding. So on a more serious note, what I'm going to try to do is provide a basic introduction to materials made of light while drawing connections to condensed matter physics. So what this means is that we'll have nice physical, mechanical kinds of analogies to understand what's going on, but at times the level of complexity and sophistication will go up as we try to draw some deep connections. I'm very happy to have you ask questions at any point here, but I don't want people getting stuck and feeling frustrated if there's a bit that's hard to wrap your head around or too technical or something. I want to put it in here for experts, because I know everyone's an expert in some particular area. But if it seems extremely opaque, it's probably not going to be central to what I'm talking about moving forward. So you don't have to get wrapped up in it, don't worry. I'm going to try to bring everyone along through this whole thing. Okay, so I wanted to start just by asking this question, what is a material? So what I'm going to show you here is sort of a classical analog of a material. Each one of these little blue dots is a particle, by which I mean its energy is given by its mass times 1/2 times its velocity squared. Okay? Plus, it's kinetic energy. And additionally, at large separations, these particles are going to attract each other. And at small separations, they'll repel each other. Okay? And then the only other thing that I'm going to put into this numerical model is a little bit of friction. Okay? So what happens when I run the model? Any guesses? What? Yes, exactly, but more than that. It's quite neat. So you run it, and you just wait, and you get a crystal. Right? And indeed, you can see the excitations or phonons. We could play the whole condensed matter game in this little numerical model, the classical condensed matter game anyway. Okay? And all we had to do was create some kind of an object that we call a particle. That is to say, it has some relation between its energy and its momentum, right, or its energy and its velocity. And we need some interactions between the particles, okay? And we need something to take out the extra energy so that they can clump and not just bounce around forever, okay? And the one essential ingredient on top of this is what I would call a classical material, is that quantum mechanics needs to play an important role at the end of the day. So these particles can have perfectly well-defined position and momentum, okay? If one starts to go to a regime where the mass of the particle is small enough, then quantum uncertainty starts to come in and the particles can become entangled, and so forth. So, with that as a backdrop, today's story is going to focus on collections of particles and what it means to make a photon behave as a particle. And the next talk, we'll talk about making these photons interact with each other and how they can then order. Okay? So this is the first two, making photons behave as particles, either in the optical domain or the microwave domain. And we can think of this equivalently as controlling the dispersion relation of photons. Tomorrow's story will be about making optical photons interact with each other or making microwave photons interact. And then what I would like to do on Wednesday is kind of give you an overview of the places that folks have imagined this science going and how it relates to the numbers in the system. I know I said I was going to start with the numbers, but I kind of felt like going in the other order might be a little more physically motivated. And the sorts of condensed matter physics problems that we're hoping to address here in the future. This is a model of a wormhole that we're exploring, building up to exploring the lab right now. Okay. So the first bit of this talk is about controlling the dispersion of individual photons, making them behave as particles as we understand them. So this is a lot of introduction prior to talking about the science, but to be totally honest with you, I almost feel like the introductory material is more important than the technical details, so bear with me a little bit. So why are we bothering to make materials out of light when one can make them out of electrons in an ionic crystal? That's pretty easy, right, at some level. Or cold atoms in a lattice, a little bit more tricky, but you get really fascinating science out there. So why bother with photons? Well, a piece of the answer is that the models that are easily accessible can be quite different from the models that are easily accessible with either electrons or cold atoms. And so we'll see some of these exotic models that one can make. Again, the photon wavelength that we're going to work with is in the micron range to centimeter range, meaning that it's much easier to kind of detect and image these systems than solid-state materials. And the dynamics are sort of in between, in time scales, what you get for electrons, which is attoseconds, femtoseconds, and what you get for cold atoms, which is milliseconds to microseconds. And so maybe we can hope to get a little bit more dynamics, run the experiments a little faster, it's a little less painful for the graduate students. I'm not a graduate student anymore, so that isn't a priority for me. But anyway, one other thing I think that's sort of interesting here is when you really run the numbers, optical photons, or excuse me, microwave photons at least, are no more open than cold atoms. But the things that are easy to do with them are sort of different in terms of the cooling techniques we can bring to bear on them to suck entropy out if we want to. Are, I would say, more powerful for photons, but it's much harder for us to change our Hamiltonian in real time. Okay, but we'll come to that later. All right, so the story today then is going to be talking about cavity photons as particles in sort of a continuum limit, and microwave photons as particles in sort of a more lattice region. Okay? So, there are a whole lot of different people who mean a lot of very different things when they say, I'm going to make a material out of photons. Okay? There have been experiments where people have Bose-condensed photons, coming from folks like Martin Weiss. There are experiments where people hybridize photons with electronic excitation, make things called exciton polaritons, and they can Bose-condense those. There are experiments of photons in 1D tubes colliding with each other and starting to order. Folks like Tilman Esslinger and Ben Lev talk about super solid phases of photons and cold atoms interacting with each other. people do cavity quantum optomechanics with a combination of photons and atoms. So it can mean all sorts of different things to different people, and the reason is that photons move at the speed of light fundamentally, right? So the way that you slow them down, the thing that you use them for can be any of a variety of different things, and it means different things to different people. I'm going to be very concrete in what I'm telling you about all this week, okay? I want to think of a photon as a massive particle that I can trap, that I can apply magnetic fields to, that I can lead to collide with other photons and to form crystals, or to form fluids, or to form topological fluids. Okay? So this stuff is fascinating, but it's not really the story that we have in mind. Okay? So the central premise of this story, and now we're getting to the meat a little bit, is that a photon in a multi-mode optical resonator behaves as a massive particle in a harmonic trap. So what should that, how should we understand that analogy? Well, what I want you to think of is shining a beam of light into a cavity. So I have these two mirrors that are highly reflective, okay? And I'm going to shine light into this cavity, slightly off of the cavity axis. And my claim is that this light kind of bounces back and forth like a massive particle in a harmonic trap. Well, what does that mean? We can be very concrete and just trace the ray as it bounces back and forth in this cavity, right? And what you see immediately is that basically the photon doesn't move up forever because the curvature here kind of refocuses the light, traps it in the transverse direction, and pushes it back downwards, okay? What you can also see is if you just watch in the middle of this cavity, okay, where the photon hits this central plane, okay, the hit patterns are very closely spaced here, and then they get more widely spaced and get more closely spaced at the other end. So for those of you who've taken some advanced classical mechanics, this looks very much like the Poincare section of a classical harmonic oscillator, right? Or equivalently, you can say, if I have a strobe light and I have a particle oscillating in a harmonic trap, you would see close together spots and then get further apart and closer together. Okay? All right. We can now go to kind of more of a wave picture. I don't want to call it a quantum mechanical picture per se, but a wave picture of this story. Okay? What are the eigenstates of a quantum harmonic oscillator? Well, they are Hermite-Gauss modes in space, and they are uniformly spaced in energy. Okay? For anyone who has ever built a laser, who's built a laser? Was it a gas laser? Or a dye laser? Okay, I guess none of us. Have you built one of those? I've never actually built one of those. Yeah, okay. So, but if you have a macroscopic cavity, okay, you can see these transverse modes are Hermite-Gauss in space, and they're uniformly spaced in energy. Okay? In fact, if you've ever built a Fabry-Perot, just with two mirrors, you get to see this. Okay? And so, at some level, you can see that there's a very clear analogy between the modes of an optical cavity and the eigenstates of a quantum harmonic oscillator. So how should we understand this physically now? What I want to do is inject light a little bit off center, okay? And that should create a wave packet in the cavity that's displaced a little bit. And I can write that wave packet for now as the superposition of the lowest mode of the cavity and the first excited mode in the transverse direction, okay? And these have different energies, just because they're different modes of the cavity. And so what that means is that sometime later, this e to the I omega t will be an e to the I pi, which is -1, which turns this plus sign into a minus sign. So now the photon is displaced to the left of the cavity axis instead of the right. Okay? And so this is how this photon oscillates back and forth in the cavity. And indeed, for those of you who have taken a quantum mechanics course, which hopefully is most of you, you've seen this story before, but it was for a quantum harmonic oscillator, right? So I guess all that I'm trying to say is, I say that this is an analogy But in some sort of a very sharp sense, a photon in a multimode optical cavity behaves exactly as a massive particle in a harmonic cavity. Yes?
So can I understand this as you have a massless particle in 2D with these boundary conditions of the mirrors, and you're tracing out basically one of the directions?
Yes.
And in just one direction, it looks like a massive particle.
That's right. So the basic point is you can't really change the speed with which a photon propagates, right? It always moves at the speed of light. But if I apply a force transversely, I can tilt its trajectory a little bit. And as long as that tilt angle is small, I can Taylor expand basically what happened, what the relationship is between the energy and this transverse momentum, and you get a quadratic. Okay? The picture you should have in your mind is that the photon is delocalized everywhere along this cavity axis, okay? And oscillating back and forth in the transverse plane. Now, I have completely ignored the fact that an optical resonator has modes in this third direction, right? So the point is we are picking a single longitudinal load, any one that you want, and thinking only about the transverse modes of the cavity, okay? For those of you who like to think about Cloquet pictures, do we have anyone who likes to think about Cloquet? Just, okay. No offense, but you don't count. we can talk there, but blue shirt, I'll go through it very briefly. So the picture is, if I think of light at some plane in this cavity, I can think about how it propagates through a round trip and generate what looks like kind of a Cloquet Hamiltonian, thinking of the mirrors as basically periodic drives on this wave function. Okay? And so what you can see is propagation along the length of the cavity gives me e to the I kz times L. But kz is really k minus kx. There's an extra L here, I call it kx squared. And so you can see that propagation along the cavity gives me something that looks like free particle propagation. Reflection off of the mirror gives me a modulation of the wave function, a phase which depends quadratically on the position, and then I can generate on a round trip some Cloquet Hamiltonian, which is the log of this horrible looking object. But the truth is that because all of these terms are at most quadratic, it's quite straightforward to take this log with Baker Campbell Hausdorff, and you can actually derive what the Cloquet Hamiltonian is for this system. Okay, great. And one can go to higher order terms, and I've tried, and it gives me nightmares. So if someone wants to work on this, please let me know. Because I'd love the answer, but I don't want to do the calculation. Okay, but so what's the story here? The story is that the propagation of the particle along the cavity axis kind of maps the tilt of the ray to the amount that it gets displaced per round trip. So that's kind of like the mass of this photon. The curvature of the mirror tells me how trapped these photons are. Okay? And these are two of the simplest quadratic terms that you can have in a Hamiltonian. The question is there a way to add the only other sort of interesting quadratic term that there is, which is a magnetic field? Is there something we can do to this cavity to make a magnetic field for light? And what I'd like to show you is that twisting the cavity does exactly that. Before we do that, we have to take a step back and talk about World War II submarine movies. So, has anyone ever seen a World War II submarine movie? The periscope and the, right? Did you ever wonder why they don't just rotate the top mirror? Why isn't there just a crank? I look here, rotate the top mirror. Right? Why does the whole thing have to turn? So Emmanuel's laughing because I've actually stopped giving this analogy normally in my talks because I've given it for so long. But none of you have seen my talks before, so I get to give it again. It's great. So why can't you do that? Imagine you have a periscope like this, and you're looking at a tree. Okay? The periscope is just two mirrors. The light comes out at the bottom, and the tree is right side up. But what if I rotate the top mirror by 90 degrees? relative to the bottom here. Well, what happens is my tree comes out sideways. Okay? So this is not a great thing to do when you're in a submarine, the world sideways. But the point is, this is very nice for a cavity, because you can imagine making a cavity with some twist like this, and then just 2 more mirrors to close the round trip path. Okay? And then on every round trip through the cavity, the ray trajectories get rotated a little bit. Okay? So you make some cavity like this, and the ray trajectories get rotated around the axis. So what do we know about what happens when we live in a rotating frame? Well, we get fictitious Coriolis and centrifugal forces if the rotating frame is not the real frame, right? If we're looking at inertial physics and a frame that's rotating around it, we get fictitious forces. But the point is, in our lab frame, the hit pattern is getting rotated. So these forces are now real. So you create a Coriolis force on the photons and a centrifugal force on the photons. And this centrifugal force is just a radially outward force. And this Coriolis force looks just like B cross B. Gives you a Lorentz kind of a force on your photons. And this one we can just cancel with the mirror curvature, right? So up to talking about these 4 mirror cavities, this is exactly the analogy that's used in exciton-polariton condensates and photon BEC experiments. The essential idea is that you trap your photons in this cavity, and you get massive particles in a harmonic trap. And you can get them to thermalize with one another in some way. And we'll talk about that more tomorrow. You can get them to Bose-condense. The new ingredient that one can add here is these Coriolis or centrifugal force terms. And this allows us to explore things like topological physics. So the picture you should have in your mind now is that such a cavity without a twist looks like a 2D quantum harmonic oscillator. Okay? That is to say, the eigenstates, the lowest eigenstate is this harmonic oscillator ground state, and we have excitations along x and along y. And we have a manifold of degenerate states with 2 excitations, one along x and one along y, or both along x or both along y, and so forth. So what happens is we start to twist this thing? Well, you add a magnetic field to your problem. And when you add a magnetic field to your problem, on every round trip through the resonator, the state gets rotated a little bit in space. Okay? So the question is, can this be an eigenstate in a twisted cavity? Well, no, because under a round trip, this 2-lobe structure will rotate, right? And if it doesn't go back to itself, it's not an eigenstate. But so the point is, a superposition of these two, this one plus I times that one, or minus I times that one, is an eigenstate. It's a ring. Okay? And that ring has a phase winding. And if that phase winds with the rotation, then the energy goes down. If it winds against, the energy goes up. So as I start to twist this out of the plane, what you'll see is that the eigenmodes will become these rings. And one will go down in energy, and the other will go up in energy. So this is theory to this point. But the point is you can build a manifold of essentially degenerate states in this way. Does anyone know? Well, yeah. This is called the lowest Landau level. Okay? From condensed matter physics. And so, but the point is that this is not, there's nothing magical about how one gets the lowest Landau level. If you go through the math for how it's done in a condensed matter physics book, it's dressed up a little differently, but it's more or less the same math with the same physics.
Does your system size correspond to a cavity
length? Well, it's interesting. The cavity length essentially integrates out of all of these stories. We ignore it, right? The essential picture is the system size is the transverse size of your mirrors.
So the other three. Okay, I see.
So, to be clear, two mirror cavities for a minute that are more typical. The photons are bouncing back and forth like this, but what we're doing is thinking about some central plane here, and thinking of this as just a particle that moves along like that. Okay? And so the point is, the length of this cavity controls, essentially the mass of the photon, right? Because the longer the cavity is, a small tilt of the wavefront corresponds to a larger displacement, and hence a lower photon mass, right? But the real space physics, if you will, is just determined by the length of this transverse range. Okay? Yeah, okay, great. And so this is where a sort of miraculous, yes?
What is the factor that decides the degeneracy in the Lewis Landau level, like experimental?
Experimentally,
Yes.
okay, we can go into this. This is sort of a neat thing. So let's first talk about a two-mirror cavity. Okay? The first question you should ask is, how big is the lowest spatial mode in the transverse direction? Right? It's going to be a Hermite mode. And you have to figure out how big that mode is. And so I don't know what your background is, but basically you can use ABCD matrices or whatever you want. But basically you're solving a boundary value problem to figure out how big this mode is. Yes? And so if the radius of curvature of these mirrors is r, and the length of the cavity is about r as well, then the size of this lowest mode is about r lambda over pi. Okay? Now, so that you can think of now as the size of this lowest Landau level, lowest angular momentum state. And you just ask how many of those either fit on your mirrors or fit before the paraxial approximation breaks down, or before the quadratic approximation to the mirror shape breaks down, whichever comes first.
So basically it depends on the number of transverse modes you initially create by those pieces.
Yes. And once we add interactions tomorrow, then whatever is mediating the interactions will also affect the system size. So that's the size of the atomic cloud and the size of the laser beams dressing the cloud and so on and so forth. But at lowest order, if you don't want interacting physics, and to me, this is sort of the amazing thing about doing this stuff with photons. You can get all the way to Landau levels just with 4 mirrors. It doesn't have to be in vacuum. It doesn't have to be cryogenically cooled. The photons don't have to be interacting. And so this is very nice. It substantially simplifies doing the science at some level. My attitude is that atoms are hard, laser-cooled atoms are hard, and so you should use them for as little as possible. And so we use them for the one thing that nothing else can do, right? Which is mediating interactions between these photons, right? And breaking time versus entropy in the cavity, and dissipatively stabilizing the many-body states. It turns out you need them for a lot of things. And I kind of play around. I am an atomic physicist, right? It's my bread and butter, what I love. But if you can simplify your science, that's always good. And so the data I'll show you later applies when we put one photon into the cavity, or when one puts one photon into the cavity. But we do these preliminary experiments with billions and billions of photons, which makes it much easier and quicker to explore the properties of the system. Okay, so the first surprise comes in. These modes stop looking round when you make them degenerate. Weird stuff starts to happen to them. You're doing great on that. So we started late. Does that mean we finished late? Or I just talk less?
You have about half an hour.
Good, perfect. So why are these modes not round? Well, when you stir Bose-Einstein condensated atoms, okay? There was an early idea that a good way to explore fractional quantum Hall physics was to take a Bose-Einstein condensate of atoms, okay? So this smudge on the floor can be our Bose-Einstein condensate. And then we saw here that rotating the photons creates a gauge field, right? So what people said is, what happens if instead of rotating the atoms, we just rotated the observer? Right? Well, it turns out that now you have this synthetic magnetic field in your problem, in the rotating frame. You're also getting pretty dizzy. You notice I'm standing very still right now, and that's why I'm pretty dizzy. But the problem is the system is nowhere near the lowest angular momentum state in that rotating frame. Okay? Basically, the atoms are stationary in the lab frame. You're rotating really fast relative to them. So basically, effectively, you've injected a lot of angular momentum into the system. So now you need to stir the atoms up to your rotation speed to take that angular momentum out. Okay? And what people always found is as you stir faster and faster, when the stirring rate gets just to the point that this physics should take off, everything falls apart. The atoms fly away. Why do they fly away? Well, the picture is this. The trap that your atoms live in is never perfectly round. And indeed here, when I'm stirring them, I've made it intentionally not round, because my stirring paddle kind of makes it a little bit oblique. Okay? And so the point is now, when I get to this degeneracy point where I should have a Landau level, what do I actually have? Well, remember the point was that how fast did I have to rotate? I had to rotate fast enough that the centripetal force exactly canceled the harmonic confinement. Okay? But the point is, if my trap is elliptical, there's no speed at which the confinement is precisely canceled, is there? It can be canceled along x, but not along y. So generically what you do is you create some kind of a saddle potential. And what do we know about electrons in magnetic fields? They love to live on equipotentials, right? And the equipotentials for a saddle all go off to infinity. Darn, right? So what happens experimentally is right as you get to the point where you should see your beautiful topological quantum physics, all of your atoms leave the trap. And you see the same thing actually for photons. So this is in some ways kind of not ideal. So partially I'm telling you this story because there's a neat solution for photons that doesn't really exist for natural particles. But partially I'm telling you this story to share the connections between these different platforms, right? Electrons and atoms and photons, they're really sort of qualitatively not so different. All right, so how do we solve this? Well, the point is this residual harmonic confinement looks like x squared minus y squared, okay? Because we canceled out most of the trap, we're just left with this x squared minus y squared bit. And so that drives transitions that exchange 2 units of angular momentum with the atoms, or with the photons in this case. So what if we could make a Landau level that only had every 3rd angular momentum state? Okay? That'd be very nice, but how can that be a thing? Well, the picture is this. Up until this point, in our Floquet story, or in any of our physics, we only talked about a single longitudinal mode of the cavity, and we cared about the transverse quantum numbers. Okay? And we made this lowest Landau level, L equals 0, 1, 2, 3, 4, 5, and so forth, going up, out of modes of a single longitudinal manifold. Okay? That is to say, all of these eigenstates have the same number of nodes along the cavity. But so say maybe these are macroscopic cavities and the wavelength of light is like a micron. So say this is 100,000 nodes. This has 101,000, or 100,000 and 100,002, and so on and so forth. So we have many copies of this lowest Landau level. For those who think about Floquet, you can think of these as the Floquet copies. But here they're actually at different real energies because the Floquet is not really okay, it's in space rather than time. Okay? But what we can do is now keep twisting the cavity. We made all of these states degenerate. But what if I keep twisting? Well, now I can create a situation where the L equals 0 mode with 100,000 nodes is degenerate with the L equals 3 mode with 100,001 nodes, and the L equals 6 mode with 100,002 nodes, and so forth. So these other states, I've made them pale, but there are a lot of other states around, and this is sort of generically the challenge with Cloquet science, right? If you're not careful, all of these other states that I've made pale appear on top of your states of interest and disturb the physics. But if you're careful, now you have a system which only has L equals 0, 3, 6, 9, 12, 15, 18. So first you say, yes, that's great, we did the thing we wanted to do. And I'll show you data in a moment that we can do this and it works great. But it wouldn't be crazy to say this is not a Landau level. Right? You'd be correct, right? A Landau level has every angular momentum state. The neat thing is that this object is a Landau level on a cone. So how can you understand that? Well, what I'm showing you here is if you create a cavity with this geometry and you just ray trace like we did on that third slide, and follow the photons around this cavity, you see that on a round trip, it doesn't come back to this cyclotron orbit. On one round trip, it appears on a second cyclotron orbit. And then on another round trip, it appears on the third one. And then it comes back to the first one. And so we get sort of 3 copies in space of the same physics happening over and over and over again. So why is that a cone? Usually I would have a sheet of paper for this, but we'll survive without it. So the point is, if I take a cone can be made out of a sheet of paper. And anything that can be made out of a sheet of paper without crumpling is flat in terms of the curvature of the surface. Okay, the only place where this has curvature is the cone tip. Because if you want to make a cone out of a sheet of paper, you would better make sure that you wrap it around this point. You don't have the cone tip actually be on the sheet of paper. Okay, so this system has curvature at that tip. Okay, but let's say I unwrap this cone and I see that it's a third of the plane. Well, now the point is, when I leave this third, I had better come back in over there, or I'm not living on the surface of a cone. But the 3 copies gives me precisely that. If I have 3 copies of the same physics and I only look here, then when I leave here, I'll come back in over there. Okay? And there are all sorts of sort of fascinating implications of this. But what I'll say for now is we can make these structures. We put mirrors into some 3D printed plastic thing to get the mirrors aligned to each other properly. We can get the modes degenerate to a megahertz or better, which means that when we add interactions between our photons, those interactions only need to be on the megahertz scale. And I'll show you tomorrow that actually we can see the angular momentum changing collisions, indicating that we're starting to make this conical Laughlin state. But fundamentally, this all works. And one can measure the Chern number of this thing. If anyone's interested in that, it's a rather technical but neat story. We measure the Chern number in real space with Kitaya's formalism, so just grab me at lunch or afterwards we can talk about it. And indeed, there are some features that relate to the curvature that are sort of fundamental to this platform. There are proposals that one can essentially see an analog of coupling to magnetic fields, so charge, that couples to curvature. And so we measure this analog in this platform. And again, I think probably I'll skip this piece of the story. But my hope is that has kind of introduced some of the cool science one can do here. What I want to do with the remaining time is first take a 1-minute break, well, maybe 10-second break. You don't get to stand up. And then we're going to go on and talk about using microwave photons to make materials and lattices, and that's sort of more analogous to what you heard from the manual. This is my cat, Penny. I have an app on my phone that I set up a camera in my house, so I can tell you that she's 100% alive as of 45 minutes ago. Her automatic feeder fed her. So, relax your brain a little bit, because we're now going to do a rather different implementation of single particle dynamics for microwave photons. Okay? Oh, you've heard what's happening now. Great. All right. So, we have this kind of crystalline regime. And here, so far, we've been talking about photons living in the continuum, okay? And that we'll eventually want them to interact with one another in the continuum in order. But if you go back to Emmanuel's talk, he was talking about lattice physics. Okay, so what's the point there? When you write down this Hamiltonian, there are two terms. Okay? This first term is a sum over neighboring sites of a term that destroys a particle on site J and creates one on site I. So this lets individual particles hop from one site onto their neighbor, onto the neighboring site. Okay, so this is the single particle physics that corresponds to the sort of p squared over 2m dispersion of a massive particle. But this is the lattice version of it. Okay? And then this potential for particles as a function of distance, attract each other at long range, repel each other at short range, has an analogy here as well, and that's this term, which is a sum over sites of the number of particles on that site times the number of particles minus 1 on that site. And this is sort of the simplest nonlinear term that one can imagine. So what is the value of this if the number of particles is 0? Well, this is 0, so the value is 0, right? What's the value if the number of particles is 1? Well, now this piece is 0, so the value is 0. Okay? If it's 2, well, then we've got 1/2 times 2 times 1, so it's u. Okay? So for those who haven't seen second quantization before, this is sort of the qualitative connection between a second quantized lattice story and a continuum picture. And I say picture in the most concrete sense. Okay, great. So the question is, how does one explore this kind of physics with photons? This slide is not supposed to be in there at all. So the basic idea, and this is what I'll show now, is that you can think of a resonator now that has only a single mode as a box that can hold photons. Okay? And the amount of energy in that resonator is the number of photons in the box times the energy of one photon. And now, if we want to have photons hop from one resonator to another, we just have some object that connects them. Okay? And if we make a whole chain of these resonators, this makes a lattice. Okay? Sort of simple qualitative picture of what's going on here. And now we just need to talk about what kind of physics we want to study and then how we can implement that. So let's go back to magnetic fields for a moment. Okay? So in the continuum, what do particles do in magnetic fields? Well, they go in little cyclotron orbits, right? If your system has an edge, your particles try to go in cyclotron orbits, okay? But the cyclotron orbits reflect off of the edge of the material and turn into these skipping orbits along the edge. And the neat thing here is that if you add a defect into your system, your particles will be able to go around it. So the reason I'm mentioning this now is because in a lattice, it's a little bit more difficult to measure the single particle orbitals. Okay? They're not as clean and beautiful and smooth as they are in the continuum. but seeing this single directional disorder immune edge orbit is actually much easier in a lattice system. So I'd like to talk about how we engineer this in the lattice and how we observe that physics, or how we want to observe that physics. So the question is, what does a magnetic field even mean in a lattice? So who's heard of the Harmonic effect? Stop trolling that. Yes, so most of you have. The basic neat point is that all of the physics of particles hopping around in a magnetic field in a lattice is encompassed in ensuring that the particles accrue in a Harmonic phase when they go around a closed loop. Okay? And so, how much phase should they acquire? Well, it's just the magnetic flux through that loop in the correct units. Okay? So the point is we need to engineer a situation where when a particle goes around one minimum square, it acquires this much phase. That's just a number in units of pi. Okay? So how do we make that happen? Well, let me write out a Hamiltonian that does it. And I think this is, in some sense, the most important thing to take away from this piece of the story. So if you're feeling saturated, just try to absorb this, and then ignore everything else that I say for the next an hour and a half. So this Hamiltonian is a sum over lattice. And remember, we're in 2D now, so we have to have two indices, mu and nu. Okay? And the picture you should have in your mind, let's look, there are four different terms. So this term destroys a particle at site, is that above? I'm an experimentalist, a little neurotic. Okay, destroys a particle at site mu nu, and creates one up by one site, right? In the vertical direction. And then there's a term that destroys a particle at mu and nu one up. So we can either destroy one here and create one there, or destroy one here and create one there. That's these two terms. So the vertical tunnel has no phase associated with it. So that's all of these vertical links are described by these two terms. The action is in these two terms. Okay? This term destroys a particle at our site mu nu and creates a particle one site to the right with a phase of e to the I alpha nu. So that is, and this is just the Hermitian conjugate of that. So, but this is the interesting piece. The amount of phase that I get when I tunnel in the x direction, okay, depends upon which row I'm in the y direction. Okay? The further down I am, the more phase I acquire as I tunnel in the x direction. So, how does that implement my Harmonic phase? Well, let's follow a particle around a little loop here. Tunnels vertically, I get no phase. Tunnels horizontally here, and I get a phase of alpha times nu plus 1. Tunnel vertically, no phase. And then I tunnel horizontally, and because I'm one row up, the amount of phase that I lose is 1 alpha less than it was before. And so this total is alpha. And indeed, if I do 2 Placats, I will acquire twice the phase. Okay, so fundamentally this is called the chiral substitution. And all of the physics in the lowest band in the magnetic field is described by this. So how do we realize this physics in an experiment? Well, the basic point is photons are not charged particles. So if you apply a magnetic field to them, they don't experience an Aharonov-Bohm phase, right? We need to somehow induce this Aharonov-Bohm phase. Well, one way to do it is put them into these twisted cavities. But now we want to do lattice physics, so we don't have that at our disposal. The most natural thing to do comes from John Tronopoulos and Maren Soljacic at MIT. They say, what does experience magnetic fields? Electrons. Okay? So the simplest thing you can imagine doing is put an electronic material in a magnetic field, okay? And then couple the electrons to your photons. Okay? Don't think about Peierls phases, just brute force. And as long as the momentum of the electrons couples to the momentum of the photons, they can see these bulk bands and these edge states that live between them that propagate around the edge of the system. So this works. It's not the Peierls substitution, but it does work. The problem is these materials are very lossy. And as we know, you need to maintain your particles for a long time so that they can collide a bunch of times if you want to study many-body physics, right? So this is not ideal, and indeed the other two stories I'm going to tell you here are not ideal for that. But these two are sort of closer to the kind of science that we want to talk about. So I'll walk you through these as well. Another way to break time reversal symmetry, or equivalently to sort of generate this rotation, is by periodically driving your system. If you want your particles to go only in circles in this direction, and never in circles in that direction, you can imagine allowing them to hop here, and then allowing them to hop here, and then allowing them to hop there, and then allowing them to hop back. Okay? And if you do that over and over and over again on a lattice, and this is what they've done here, you can, again, effectively generate this spiral space. What I want to tell you about is something which is most analogous to this work from Mohammed Hafezi at the Joint Quantum Institute in Maryland. There, the basic idea is to trap your photons in little resonator rings like this, and to couple one ring to the next with a phase that you can control. Okay? So this is sort of a predecessor to the physical implementation that I'm going to tell you about. The only downside here is that these little silicon microrings are also fairly lossy. And it's very challenging to get a single emitter into them that allows you to make the photons interact. So, how does one do this? Well, brute force. So this is this topological circuit. And the basic picture is that each one of these little cavities can hold photons. And the photons can hop from one cavity to another. And we've engineered this Peierls phase into the hopping matrix elements. So how does that work? Well, we need several elements to make this go. Okay? One element is we need a box that holds photons. Okay? So that's a resonator. The simplest example of a resonator like this is basically this lidless design, which makes it easy to build. You can think of this as like a BNC cable, okay? A coaxial cable. This is the center pin, this is the ground, and the cable is shorted from the center pin to the ground at one end and open at the other end. So that makes this object a quarter wave resonator. Okay? And the neat thing is that as long as you make it narrow enough up above, the photon cannot leak out at the top. Okay? So this design is actually from Yale originally. And Rob Shulkoff uses these cavities in his cavity QED, or circuit QED quantum computer architecture. Okay? So this holds our photons. They can live a very, very long time in here. We can see Qs up to 200 million. Great. This is an artist rendition. The artist's name is John Simon. That's why it's not very pretty. Okay. So how do we implement any of this chirality that breaks time reversal symmetry here that gives us our Peierls space? Well, imagine I take one of these cavities and I put 3 posts in it. This is not, I'm very sorry guys, put this down the way it is. Yeah, I guess this is a fine way to do it. The basic picture is that if I put 3 posts in one of these cavities, the photon can hop from one post to another. And so there are 3 of them, and so this is a 3-site tight binding model. And so this cavity supports 3 modes. One where all the posts are oscillating together in phase, one where the excitation kind of oscillates around clockwise, and one where the excitation oscillates around counterclockwise. And the tunnel coupling between the posts determines the energy difference between these 2 and the third one. But what we need to do is use just one of these so that our system has some circulation in it that can give us this chiral space. So how do we do that? Well, we put a yttrium iron garnet sphere in the cavity. And basically the idea is the magnetic field for the blue mode rotates this way, and for the red mode it rotates the other way. Okay? And so if we can apply a magnetic field to this stereomagnet, it will couple only to the blue mode and not to the red mode. And split the system out and leave us with a px plus IPY orbital and no px minus IPY. Okay? So, the last thing we need is a way to couple photons from one cavity to another. So what we do is we drill a hole in the structure. Like the most boneheaded thing you could imagine, right? And at first you say, well, this can't possibly work, because now the photon can leak out down here. But the key is that the same thing that kept the photon trapped in this cavity prevents it from leaking out here. This has to be narrow enough that the photon can only leak out evanescently. That's its suppress. Okay? So great. So we can build up these lattice models. And we're now in a place to build this into a whole system. And so the picture you should have in your mind now is the lattice is going to be one of these px plus IPY sites, and then 3 of the regular sites, and then another px plus IPY, and then 3 more regular sites, and so on and so forth. This is what the physical object looks like. And now you can see why it's very important that we be able to make this from just the top and the bottom. Because we design this, and then we send it out to a machine shop to make very precisely. And one of the big challenges is all of these cavities have to have the same resonant frequency, right? But now that challenge has been mapped onto machine tolerance. And so if you pay more money, you get a more precise lattice. Anyway, this makes this story very easy. How does this give you a chiral space? Well, the picture is this. These orbitals have a 2-pi phase winding as you move around the site. Okay? So if I hop around this set of 4 sites, which we call a plaquette, then when I hop from this site to that site, I acquire no phase. When I hop from here to there, well, you can think of this as having a phase or not. It's sort of up to you. But the basic point is hopping from here to there, the photon had to go through 90 degrees in this cavity, right? It goes around and around and around in the cavity, and every time it goes around it gets 2 pi of phase, which is the same as 0. But in going from here to there, it accrues that extra pi over 2 of phase. So going from here to there is pi over 2, and then going back up to where I started is another 0. So this gives me my chiral space. But the really interesting thing is that the chiral space essentially lives in the on-site orbitals rather than in the couplings between the sites, right? Now, fundamentally, the point is we should be indifferent to what gauge we're operating in when we do electrodynamics, and this is just a manifestation of that state. Right? All gauges are the same. All right, great. So we built this object. This is what the band structure should look like. This data underneath here is what the band structure does look like, and we can see these edge modes living between the bands. And then we can do something very neat, which is we can probe every single lattice site in real time and inject light at some particular site and watch what happens. So this is watching in real time. This whole movie is about a microsecond long. And you can watch the excitation run in one direction around the edge of the system. Okay? And this is this chiral edge dynamics that I was mentioning earlier. It makes it about once around the system. And when we make the system cold, basically it goes around and around and around. Okay? And so we're now, as I'll tell you about tomorrow, we're now integrating things into this system that allows it for this. But more broadly, the point here is that this lattice analogy that one can think about for cold atoms. I don't know, were you talking about gauge fields at all?
Maybe.
Maybe.
Oh, yeah.
So, you know, essentially, once you've figured out what the correct mapping is onto photons, the physics is exactly the same whether you talk about photons or photonic atoms. Okay, so how are we doing? For anyone interested, there's a whole other story that one can tell about Weil semimetals. But the essential point is that the story sort of follows the same formula that I've told you about over and over and over again. You have some Hamiltonian that you want to realize, right? It corresponds to some kind of a tunneling matrix element from site to site. You have to define an object, which is your site that can hold a photon, okay? And then you need to get the phases of the tunnel couplings right. So one way to do that is with a circuit. Another way to do that is by machining some crazy mechanical structure, and this is how Martin Soljacic does it. Another way to do that is with these little twisted waveguides. This is how Maxim does it. But the single particle physics with photons is in some sense very, very simple to implement. And any model that you theorists can think of, we can basically realize in the lab using this kind of technique, as long as it doesn't include interactions between the photons. Tomorrow's story will be about what happens when you do include interactions, and that, I would say, is where the intellectual frontier of this photon. Okay? I'm done.
More experimental question for the microwave part. How is the observed part there working in the microwave part? Do you do it with a lot of photons?
So in the experiments I shared today, we do it with a lot of photons. And the essential trick is that you add an antenna into each of those cavities that couples to it very, very weakly so that it doesn't spoil the state. And then you can just switch between the cavities. And the point is that, in some sense, and this is what I think is really cool with photons, right? Like cold atom people at the end of the day do the readout with photons always as well, right? Well, why is that? Because the tools for multiplexing photons are really, really good. Because photons are what we use, you know, to look at things, they're what we use to communicate and so forth. So, you know, a CCD can read out many millions of channels all at once. It's a little bit more annoying for microwaves, but microwave switches can switch between many channels very rapidly. And so, in some sense, the same sort of natural control advantages exist for the materials on the photon side that exist for cold atoms. It's just that there's one less step removed, right, between the physics that you want and the photons that you're working with.
How does the statistics of photons limit the physics that you can study?
Well, I guess I would say for today's story about single particle physics, it doesn't, right? In the interacting limit, what I would say is this Fermi-Hubbard stuff will not really be studied with photons. You know, I mean, photons are bosonic. And a question that people often like to ask is, when we make our photons interact with each other, we usually do it by making these things called polaritons, which are part photon and part atom. And then you say, well, if you use fermionic atoms, are the quasi-particles fermionic? No. Because the photons are the objects that move. The atoms remain stationary, right? So there are actually neat proposals for experimentally implementing a trotterized Jordan-Wigner transformation for microwave photons. There's one from Mohammed Hafezi. so that you could try to study Fermi-Hubbard physics with light. My personal opinion is that that's not promising, because the amount of time required for every traumatization step now scales with the number of particles in your system, right? And you're like, if you're going to do that, all of the speed-ups that you thought you were going to get from quantum simulation as opposed to using your computer start to go away.
So it doesn't affect at all the gauge field state, right?
So this is a fascinating thing. The basic point is that in the fractional quantum Hall regime, you're not filling your Landau level, fundamentally, right? There's no such thing as a filled Landau level for bosons. Because you can have multiple bosons in the same state, right? So in some fundamental sense, the integer quantum Hall effect does not exist for bosons, right? Because there's no Fermi surface, right? But the fractional quantum Hall effect is about a partially filled Landau level that becomes incompressible not due to statistics, but due to interactions between the particles. And
what about with the boson in one state filled band? That would also be
yes, but then I think the point is then it's the interactions again that are giving you the feeling, right? So I guess what I'm trying to do is be careful. I don't fundamentally disagree with you, right? Many of the signatures would be the same. But I guess I would say that at some level, the things become less different once interactions dominate. And then it turns out for the bosonic Laughlin states, it's at a different filling factor than it is for the fermionic ones. But many, if not most, of the characteristics persist. Yeah?
You took great care to make all the cavities equal, but if you were making them different, this would probably amount to between disorder, a very controlled disorder. So is it
Very controlled, that's so optimistic.
I'm a theorist, so.
A couple of answers there. One is, I'll talk about this a little bit tomorrow. John Martinez's group has 1D lattices of microwave cavities in the strongly interacting regime where they start to study many-body localization. Right, so yeah, and theirs is controlled.
What is actually your variation of the resonance frequencies compared to that?
Oh,
Just to get an idea of how good this is under control. I mean, if you want to get it to zero, let's say, how good is, what's delta? Is zero.
For this version of the story, we can get the disorder down to about a megahertz, and our hopping is like 70 megahertz. Okay, so it's quite good. But the story I'm going to tell you tomorrow, it's harder, right? Once the particles are interacting, now your disorder comes from the Josephson junctions, and it's much harder to get those identical. So there what we have to do is microscopy of the full coupled system and back out the on-site energies. And we do it, and it works, right? There are nice sum rules for doing it. Now, that being said, I talked to Oscar Painter recently, and he has his disorder for non-tunable Josephson junctions down to about 10 megahertz. So, it's really getting there.